So today we're going to take a look at the large language model landscape and try to understand more about them and the entire context. From my point of view, we can trace everything back to 2017, year in which Attention is All You Need paper was published, and that paper presented a new neural network architecture called transformers. Fast forwarding to 2022, we have the tweet that changed everything for us, meaning the one in which Sam Altman stated, "Today we launched ChatGPT, try talking with it here," and he shared the URL with us. Truth be told, another milestone was achieved in 2018 when OpenAI published this paper called Improving Language Understanding by Generative Pre-training. You might recognize the acronym in here, GPT. And also you might recognize one of the contributors of this paper, meaning Ilya, which currently doesn't work anymore at OpenAI. And this paper basically introduces GPT Model 1 and a new way of tackling natural language understanding. But what it meant for us as end users. I remember when I created my account on ChatGPT when it was released, I had to join a waiting list, and afterwards, after my request was approved, I could log into ChatGPT on their website and start interacting with the large language model. So the interaction was a chatbot experience. Basically, you sent a prompt to the large language model, and then you're going to receive your answer. From a high level point of view, the large language model is just a statistical text predictor. So basically, for a given sequence of tokens, meaning our prompts, the LLM is going to model the probability of that sequence in order to predict the next token, so it can output our response. And when ChatGPT was released, the filtering of the input prompts was not that harsh, meaning that you could have asked almost anything that you had on your on your heart. Right nowadays, the filtering is way more better. And to better understand what models are really doing, let's take this small concrete exercise. On the right side of the screen, we have this table with a couple of entries, and basically this table depicts the relationship between two inputs and one output. If I were to ask you to identify that relationship, after a couple of seconds, hours, or minutes, you can quickly identify that the output is actually the summation of the first input with the second input multiplied with 2. Concretely, if we take the first row, 1, if we add 1 with 4 multiplied with 2, we're going to obtain 9, so on and so forth for each entry. Now for the more mathematically savvy ones, we can even represent this relationship as a mathematical equation in which we have the dot product of two vectors, and this is exactly what models have embedded into them. Take it with a grain of salt, because this is a very simple example. Now imagine this table might have hundreds or even billions of rows, and if I were to ask you then, okay, identify the relationship, and maybe the relationship could be even more complex. A human can, spend days or even months to identify the relationship, but the models are very, very good at seeking and spotting patterns in larger data sets, right? So from a high level point of view, this is the entire gist of the models. Now coming back to our large language models, basically they are designed to process, understand, and generate human language by predicting the most statistically probable next word in a sequence. So basically they are one big prediction loop in which they receive text and output text, right? So they us as an user, we're going to send our prompt as a text. The input to the large language model is going to be text, and the output is going to be also text in order for us as an user to receive the answer. Now, truth be told, the models do not really work exactly with text. Why? Because whenever we type our question, our prompt, this prompt is broken into small pieces called tokens. They can be words, subwords, or even characters, and these tokens are then mapped to some numbers, to some integer representations. Why? Because the model is going to use those numbers to understand our prompt, right? Because it's going to do a lookup into a thing called the vocabulary. Each model has its own vocabulary, and the transition from text to numbers is done via embedding, right? Tokenization and embedding. Basically, from a high level point of view, our text is converted into numbers, and the model uses that those numbers to search to do a lookup in this vocabulary, which is basically like a table, right? Concretely, if we want to see exactly how this process looks like, the tokenization process, OpenAI offers us this endpoint, this platform, to see exactly how it looks like. Whenever we type something in this form, in this entry, let's say we would like to specify the cat sat on the, this is our prompt, we can see we have 5 tokens, and each token has a numerical representation, how we stated previously, right? So if we take a simple example, the cat sat on, this is our prompt, the large language model will try to predict the next word in this sequence, and for this simple example, the next word is mat. Why? Because from a multiple array of possibility for multiple words, meaning mat, floor, chair, table, mat has the highest probability to be the next token in our sequence, right? So the model is going to output the cat sat on mat, right, as an output. Now, two things are worth mentioning. Models are trained on vast amounts of data, and also models have vocabularies embedded into them, right? And if we take a look at this process from start to bottom, and we're going to see exactly how the transformer workflow looks like from a visual standpoint of view. If we write into the form the same prompt, the cat sat on, and press enter, we can see how the flow looks like, the multi-head self-attention. Then we're going to see the outputs of the model, and we have multiple words with different probabilities, and in this case we have the cat sat on the floor, right? It's not the mat, right? Why? Because floor has the highest probability. Now one thing that we need to understand is that models are highly non-deterministic. More exactly, they are stochastic. What this means? It means that for the same prompt they can give us different answers. Basically, the models are just doing one big autocomplete for us, and actually this is what we are doing day to day. How's your internal autocomplete work? If I were to ask you to fill this prompt with the next token, meaning peanut butter, and you need to add the next token in this sequence, most probably you're going to say jelly, peanut butter and jelly. Why? Because even if you don't eat peanut butter and jelly, you've been trained, you've seen this pattern so many times, so that jelly has the highest probability in your autocomplete engine, right? Because yeah, it's you can say peanut butter and soup, peanut butter and meat, but from a statistical point of view, those words do not make too much sense for you, right? And now let's take a concrete example, and we can try to run a model locally using Docker as a containerization technology, and I'm going to run a simple lightweight model, more exactly the one from Microsoft Phi 3, which is a mini model, lightweight model with 3 billion parameters. And basically this model was designed to run on edge devices. So if we basically, whenever we need to search for models, we can go to Olama site. In our case, I'm going to search for Phi. As we can see, Phi 3, it's a family of lightweight models. We have the mini with 3 billion parameters and medium with 14 billion parameters. As we've seen, this is the paper. It's a highly capable model meant to be run locally on your phone, but we're going to run it on our machine. We're going to use Olama to serve our model, and as I said, we're going to leverage Docker. First and foremost, we're going to start our model, and we're going to start Olama locally, and basically I'm going to use Olama image, the name of the container. I'm going to mount a volume and expose some port. If we do a docker ps, the container is up and running. The next step for us is just to load the model inside the Olama, right? I'm going to do exec. I'm going to do Olama run phi3 because phi3 is our model. Behind the scenes, we have this volume, and this is exactly the mount point in which the model is going to be loaded in. Now, one thing it's worth mentioning is that the inference is going to be done using the CPU and not using GPU. And now let's see exactly how an inference looks like. And if we're going to send a prompt to our model, we're going to do an exec in the Olama container, and here we can ask, I don't know, who wrote Romeo and Juliet. And we're going to kick off the inference, which happens locally using my CPU, and we can see in real time how the model predicts the next token, right? William Shakespeare, an English playwright, poet and actor, is the author of Romeo and Juliet, a tragic love story, so on and so forth. So as we can see, the model predicts each token one by one. Actually, behind the scenes is running a loop, right? A regressive loop in order to create our response. But we can see it's working. It's pretty fast. We didn't do anything very computation heavy, but we can try different prompts. And let me try another one, which is related to code bases, to see if our model understands code. And I'm going to write a small snippet of Python, not really a snippet, and I'm going to send this to the model if name equals, and let's see if the model knows any code. And as we can see, in this case, the model has been offers us a small code snippet. This means that he has been trained on Python code base because he understands Python, right? Now, even more, let's run the same prompt to see exactly how it behaves. We can see that we received a different answer. This means that, as we established, models are non-deterministic, right? Now let's try something more. Let's try something more interesting, and let's ask the model something more actual, like the weather. And let's ask it weather forecast now. What do you think is going to happen? The model is not going to provide us the forecast for today. Why? Because even though the model has been trained on weather data, it has a cutoff date and he cannot know the current weather data, right? The answer is a standard one. I'm sorry, but I can provide real-time or current weather data. Now this is going to bring us to the next video, in which we're going to understand how large language model can access external data like the weather forecast, and how actually function call works, and what are the stepping stones for MCP clients and MCP servers. That was it for this video. Hopefully you're going to have a clear overview of how large language models are working, and we're going to see us in the next video, in which we're going to see exactly how we can retrieve external data for our large language models. That's about it. Thank you very much. See you next time.